So I thought an interesting thing to talk about for this particular forum is this topic of self-location, because self-location is a subject that is of great interest across both physics and philosophy. The physicists use self-locating information a lot. The philosophers have a lot to say about self-locating information. So I think this is a great sort of opportunity for a really interesting conversation between those two disciplines where we can sort of learn from each other. So just to introduce self-locating credences, suppose you undergo an experiment where you are put to sleep and an exact physical clone of you is created. One copy is placed in a room with a blue door and another is placed in a room with a red door. We'll assume the clones have sort of replicated your memories and your minds and mental states, so when you wake up in one of those rooms, there's no way for you to know which one of the clones you are. So the question is, what probability should you now assign to being in the room with the blue door? And I think many people have an intuition that you should assign sort of roughly 50% probability to the blue door, since you could equally well be in either of those rooms. We can also consider variations. Maybe there are in fact 10 copies, only one of them has a red door. Many people I think would have the intuition that you should probably think blue is more likely than red in that case. We could have 1 million copies, only one with a red door. Many people I think would say in that case you should be almost certain you're going to have a blue door. So what we're doing in that case is assigning self-locating credences. Those probabilities you are assigning are your credences about where you are located in the world. When you go out to one of those rooms and check the color of the door, you haven't learned anything new about the world as a whole. What you have learned is something about your location within the world. So that's why those credences are self-locating. And so credences like these feature in a wide range of research topics in both physics and philosophy. We use them to make predictions about where we are in the cosmological multiverse. We use them to discuss the threat of Boltzmann brains, particularly in cosmological theories. We saw an example of that in Professor Guth's talk yesterday. We use them often to make predictions in the many worlds interpretation of quantum mechanics. They're also used in the simulation argument in philosophy, the Sleeping Beauty problem, and so on. So what all of these applications have in common is that they all seem to depend on the assumption that there is, at least roughly, a rationally compelling way to assign these credences. There is some way that you should assign credences in these kinds of situations if you are rational. And indeed, they seem to sort of depend on this assumption. Most of these applications are in trouble if there's no such rational way to do it. And that is the assumption I want to question today. I'm going to argue that there is, in fact, never any rationally compelling way to assign these credences. You are always free to assign them in any way that you want, and I'm going to argue that does in fact undermine a variety of applications like this. So just to be clear about what I'm talking about here, I want to make a distinction between two different types of self-location. It's helpful here to use this philosophical term of a centered world, by which I mean a pair consisting of a possible world and a center within that world. The center is just like a location in the world where you could be. So in the room case, each of the rooms is one of the possible centers. So if there's 10 possible rooms that you could be in, there's 10 different centered worlds that you're considering in that example of self-locating uncertainty. So I want to distinguish between what I call pure self-locating uncertainty, which is cases where all of the centered worlds where you could be belong to the same possible world, versus what I call superficially self-locating uncertainty, which is where all of the centered worlds you could possibly in belong to different possible worlds. There are also mixed cases. The Sleeping Beauty problem, if you know that, is one of those, but I won't discuss those today. So an example of superficially self-locating uncertainty is when you wake up in the morning and you don't yet know what time it is. So you have some self-locating uncertainty because you don't know what time you are located at. But the key point here is that, of course, in every possible world, there is exactly one time at which you actually wake up. So each of the centered worlds that you could be in this situation belongs to a different possible world, that there are none of them which are located in the same possible world. And that's important because in this kind of case, your actual location can be determined by a physical process. There are some sort of biological and psychological processes which determine when, as a matter of fact, you do wake up on any given morning. And that means that if you're trying to assign probabilities over these centered worlds that you could be in, you can just appeal to some scientific theory to tell you what those probabilities should be. So there's nothing really mysterious about how to assign probabilities here. We can just do it the same way as we would in some sort of ordinary situation where we have a scientific theory. On the other hand, the door example is pure self-locating uncertainty. All of the clones I described exist within the same world, so all of the centered worlds you could be in there are part of the same possible world. And the key difference here is that in this case, there is no physical process which decides which one you are in. There's no process by which you are dropped into one of those clones rather than the other. You just are whichever one you are. That means that the probabilities we assign in this case cannot reflect an actual physical process that picks the outcome. You cannot just read those probabilities off a scientific theory. You're going to have to get those probabilities from somewhere else. So these pure and superficial types of self-locating uncertainty are very often treated in the same way in the literature and kind of conflated. I think that is a mistake. I think we should keep these things separate because they are conceptually very different, and the origin of the credences that we're assigning really can't be the same in those two cases. So in particular, I'm going to argue that although I think there are often rationally compelling ways to assign superficially self-locating credences, there are never rationally compelling ways to assign pure self-locating credences, and so it's important to make that difference here. So to make this argument, I'm just going to consider a range of ways in which you might try to suggest that there are rationally compelling ways to assign pure self-locating credences and try to show that they don't work. So there's a sort of ongoing debate in philosophy about whether reasons for belief should be pragmatic, epistemic, or some combination. I won't take a position on that here. I will just consider both possibilities. So first off, let's consider if pragmatic rationality can tell us how we ought to assign our pure self-locating credences. By pragmatic rationality, I mean the kind of rationality involved where you first decide on some goals, and then you sort of consult your reason to determine what is the best way to act to achieve these goals. Now, you might at first think that kind of pragmatic consideration is not going to have much to do with what you ought to believe, but there is a traditional way of connecting belief to action via decision-theoretic representation theorems. So for example, in a non-self-locating scenario, maybe you're placing bets on the outcome of a process and you want to maximize your winnings summed over a large number of trials. What you can do in that case is you can go out and do either some empirical tests or some theoretical analysis to show that the best way to maximize your winnings is to choose a strategy which maximizes the quantity shown here, the weighted sum of the winnings across various different outcomes. So we can then argue it is rational in this situation to act as if you are maximizing utility with respect to the quantities pi here. So these quantities are playing the role of credences with respect to your action. So in some sense, we can say it's rational to have the credences pi to assign those probabilities to the outcomes, or at least it's rational to act as if you have those credences. So in some sense, we can get some rational credences out of constraints on practical reasoning. And people have tried to do similar things in the case of self-location as well. So if you're looking at a self-locating case where you've got some reference class of subjectively identical observers all belonging to the same possible world, a popular thing to do here is to say, well, if these people are placing bets and they place bets in accordance with certain credences, then we should just pick the credences which are going to maximize the winnings over the whole class of observers. So Bostrom and Leslie are both making recommendations of that kind in these quotes. Bostrom, for example, considers a certain case, considers a possible credence assignation and says, well, if everybody bets that way, then 90% of prisoners will win the bets and only 10% will lose. So what's happening here is these authors are taking the sort of previous decision theoretic idea and just changing the sum over trials to a sum over observers. They're noting that in order to maximize over observers, we should choose some strategy maximizing the quantity W shown here with the coefficients pi. And so they argue the rational thing to do here is to have credences pi, or again, at least to act as if you have those credences. But you might think there's something a little bit odd about that, because after all, why exactly am I obliged to maximize winnings over all of those observers? Maybe I am selfish and I only care about my own winnings and I don't care how much anybody else wins. Now, the standard answer here is that, well, all these people are subjectively identical, you don't know which one you are, and so there's no way to design a strategy which preferentially benefits you. And that is true, but nonetheless, there are possible alternatives to just maximizing the sum over all observers. So, for example, under certain cosmological scenarios, the world probably contains many Boltzmann brains subjectively identical to me. So suppose I believe one of those scenarios, and I am placing a bet on whether or not I am a Boltzmann brain. So if I'm just going to weight all of the subjectively identical observers in my reference class equally, then of course I should bet that I am a Boltzmann brain. But I might also think to myself, well, most Boltzmann brains are very short-lived. Many of them are not going to live for long enough to actually enjoy the winnings from this bet. So I might say, I actually don't care if the Boltzmann brains win the bet. What I would like is for the persisting individuals to win the bet. And so in that case, I should discount the Boltzmann brains in my reasoning, and I should weight more heavily the non-Boltzmann brains, and perhaps then in that case, I'm going to decide the rational thing to do is to bet that I am not a Boltzmann brain. So the point here is just that it doesn't seem to me that this would be an irrational thing to do. This seems like perfectly allowable reasoning. I'm not being irrational by doing that. And so we can see that in general, there are going to be options other than just maximize winnings over all equally weighted observers. So in general, in this kind of case, we are sort of free to choose any goal quantity as shown here, where we're trying to maximize the weighted sum of winnings across the observers. And we then run into a very big problem. The problem is that as soon as you choose your goal like this weighted sum of winnings you're trying to maximize, that will immediately fix what the credences are you're supposed to have. There's never going to be any role to be played by any empirical tests or theoretical analyses. The credences that you should have that we get from this method are always just going to be exactly proportional to the weights that you chose. What that means is that in a pure self-locating case, the practical function of self-locating credences is really just to record your goal. It's just to say how much you care about the various different observers in the reference class. They don't do anything other than that. And that means that pragmatic rationality cannot possibly tell us how to set them, because as Price puts it, rationality dictates choice in the light of preference. It doesn't dictate preference itself. Rationality can't tell you how much you should care about these observers in your reference class. It can only tell you what you should do once you've decided how much you care, and in this case, there's no role for it to play here. The only role the self-locating credences could possibly play is to record your preferences. So it seems to me, therefore, that pragmatic rationality cannot possibly make any distribution of self-locating credences rationally compelling. Okay, moving on to epistemic rationality, by which I mean the type of rationality involved when you are trying to have true beliefs or to be epistemically virtuous or something like that. Often one would show that some way of forming beliefs is epistemically rational by demonstrating that it is a good way of forming true beliefs. But here we run into the same kind of problem. If you just try to show that some way of forming self-locating credences is a good way of ending up with true beliefs, you can't do that without first specifying which observers you want to do that for, and we end up with the same kind of thing as in the pragmatic case. Once you've decided how much you care about the observers, that will immediately fix the credences you should have. Therefore, it's common in these kinds of cases to instead appeal to various principles, which are presumably intended to be understood as a priori principles of epistemic rationality. A common one here is Elgar's principle of indifference, which is the idea that similar-centered worlds deserve equal credence. Similar here just means they belong to the same possible world and they are subjectively identical. So, for example, Elgar is saying in the door case, you should just assign equal credences over all of the possible rooms with doors. So I grant that the principle of indifference feels intuitively compelling, but we should nonetheless be suspicious of it because there is a similar principle that we use in non-self-locating cases, which has historically not done very well. So the non-self-locating principle of indifference is the similar idea that in the absence of relevant evidence distinguishing between mutually exclusive possible outcomes, you should assign equal credence to all of them. This, I think, is also quite intuitively compelling, but it has turned out to not be very successful in the history of probability. That's because of something called Bertrand's paradox, which refers to the fact that there are different possible ways of dividing an outcome space up into individual outcomes, and different choices of divisions will give different results when we try to apply the principle of indifference. A famous example of this is Buffon's needle, where you imagine dropping a needle onto a floor with some floorboards and trying to predict the probability that the needle crosses the cracks between the floorboards. So historically, a number of people tried to solve this using the principle of indifference, and they got different results because they divided the outcome space up differently. One option is to divide the outcome space up into increments of equal angle. That will give you one prediction for the probability. Or you can divide the outcome space up into increments of equal horizontal distance. That will give you a different prediction for the probability. So there's no way to kind of do this sort of a priori. There are different conflicting results you can get by applying the principle differently. Now, you might be tempted to say, well, that's only going to happen when we have a continuous outcome space. We're fine if we have a finite outcome space. But really, in any realistic physical scenario, the set of outcomes is going to be effectively continuous. It might be described to you as if the outcome space is a finite set, but we can't always just trust the initial description of the problem as presented to us. For example, I might say to you that I'm going to roll a die and describe the outcome space as 1 or not 1. If you just naively apply the principle of indifference to the description I've given you, you will predict that that I should obtain the outcome 1 with 50% probability. That is, of course, not right. In order to know what the right partition is, you need to actually look at the details of the physical situation and understand what that physical situation implies for the right partition. And in fact, in non-self-locating cases, there is a way to decide what the right partition is. We can sort of show empirically that the right partition is going to be the one which reflects relevant features of the process which determines the outcomes. Very often, that is the symmetries of that process. So, for example, in the Buffon's needle case, it turns out that if you are dropping the needle in a way which is blind to rotation angle, then the right way to choose a partition is to do the angle partition to reflect the symmetries of your dropping. If you are instead dropping the needle in a way that is blind to horizontal position, you should use the horizontal partition instead. And so the partition which gives you the right results to match the empirical observations is going to be the one which reflects the properties of that process. So as Van Frassen puts it, this kind of method can't be applied a priori. You do need to kind of go out and investigate the physical situation and understand what the relevant features of the process are. So returning to the pure self-locating principle of indifference, the worry here is that if you can't apply the non-self-locating principle in a sort of a priori way, it's not clear why the pure self-locating one would be applicable in an a priori way either. Elgar, in his formulation of the principle, is just assuming that you should always use the partition of the outcome space, which has sort of one consciousness per outcome. And sure, that is an intuitive thing to do, but that doesn't make it rationally compelling. In the Boltzmann brain case, for example, you might instead choose to have a different partition which weights the brains by lifetime instead. And it doesn't seem to me that there's any obvious sense in which that is irrational or wrong. That is a thing you can do if you want to. There's nothing to stop you doing that. Moreover, we're kind of in trouble in the pure self-locating case, because in that case, we can't just go to look at the process which produces the outcome to know what the right partition is, because there is no such process. In the clone case, there is no physical process which drops you into one clone or the other. You just are whichever one you are. There's no process producing the outcome, and therefore we cannot just go and consult the symmetries of that process to know what the right partition is. Now, some philosophers have nonetheless attempted to justify various principles for self-locating credences by appeal to symmetries. This is particularly popular in the context of the many worlds interpretation. So there's versions of this due to McQueen and Weidman and Siebens and Carroll. But it seems to me that these approaches cannot work because the symmetries are not attached to the right kind of process. In this kind of situation, the symmetries are necessarily symmetries of the process that produces the outcome space in totality. They are not symmetries of the process that selects the particular outcome that you see, because there is no such process. So we can't go and consult the right kind of process in this situation, and so we can't have a way to show that the symmetries are in fact relevant. We can kind of see that by going back to the Buffon's needle case. In that scenario, if you just kind of look at the floor, you can see that the floor is going to have various sorts of translational symmetries, but those symmetries don't really help you to choose the right partition. What you need to do in that case is specifically look at the symmetries of the way in which the needle is dropped, of the process which is selecting the outcome of the process. If there is no such process, as in the many worlds case, or as in other pure self-locating cases, then there just isn't going to be any rationally compelling way to select a partition, and so there's not going to be a rationally compelling way to apply this kind of principle. So for those reasons, I'm pretty suspicious of the idea that there's any epistemically rational way to assign these credences either. Final class of arguments I want to consider are ones that are based on making analogies between self-locating cases and non-self-locating cases. So there's a sort of common argumentative strategy which starts from a non-self-locating case where it is presumed that the appropriate credences are obvious to everyone, and then saying, well, this pure self-locating case is kind of quantitatively or structurally similar, so you should have the same kinds of credences in that case too. So if you are familiar with it, Elgar's quantitative argument for his principle of indifference is an argument of this kind. I don't have time to go through the details right now, but I think this fails for this reason. It's kind of translating credences from the non-self-locating case to the pure self-locating case without properly taking into account the significant conceptual differences between those cases. The worry here is that since the reasons we have for assigning credences can't be the same in non-self-locating cases and pure self-locating cases, there's no really real reason why you should expect that the credences are just going to translate across in these cases, even if they look structurally similar. And so it's a mistake to think you can just kind of get your credences from a similar non-self-locating case without taking into account those differences. Another kind of analogical argument that we sometimes see involves making analogies to cases of certainty. So for example, consider the following two cases. Suppose that in case A, I know that none of the subjectively identical observers that I could possibly be are simulations, whereas in case B, I know that one of the subjectively identical observers that I could possibly be is a simulation, but the remaining 999 are not simulations. So obviously in case A, it would be reasonable, indeed I should assign credence 0 to being a simulation. What about case B? Well, case B is a self-locating credence. I therefore want to argue that you are free to assign any credences you like here. You can assign any credence between 0 or 1 to being a simulation. And you might think that's a bit strange. You might say, well, case A and case B are very similar, right? So if you must assign credence 0 to being a simulation in case A, surely you should assign credence quite close to 0 to being a simulation in case B. So you should be rationally compelled to assign that particular distribution of credences due to the sort of quantitative similarity. But as a matter of fact, I think that rests on sort of confusing two different ways of understanding the claim, I am certain that I am not a simulation. Because that could be understood as a self-locating claim of the form P1, I myself am one of the observers in my reference class who is not a simulation. But that could also be a non-self-locating claim about your evidence to the effect, my experiences are not compatible with being a simulation. So clearly in case B, where you know that there's one observer subjectively identical to you who is a simulation, then you must assign credence 0 to P2. And I want to argue that if you're in case A, if you genuinely believe you're in case A, you must believe that your experiences are not compatible with being a simulation, so you must assign credence 1 to P2. So we see that in that sense, those two scenarios are actually not that similar. They look quantitatively similar, but the nature of the evidence you have in these two cases is necessarily quite different. So I think it's actually entirely reasonable to say that the credences you might come up with in those cases could be very different. You are not rationally obliged to have quantitatively very similar credences in these two cases. Okay, so having sort of made my case against pure self-locating credences, I want to go and look at a couple of applications and see what it would mean for these applications if we agree that there is no rationally compelling way of assigning pure self-locating credences. So one application is the simulation argument. This is the argument which says we have good reasons to believe that the world contains many more simulations than actual people. Large numbers of these simulations might in fact be having experiences subjectively identical to yours, so you should believe that you are most likely in a simulation. So clearly this argument is assuming that you are required to assign credences which are pretty much equal across all of these observers. You're supposed to assume that you are at least roughly equally likely to be any one of the possible observers. But this is, I think, clearly a pure self-locating case. All of the centered worlds we're considering here are in the same possible world. Both the simulations and the non-simulations are part of the same world. And so I would argue that there is no rationally compelling way to assign the credences here. You are free to decide any way you would like to assign credences across the simulations and the non-simulations. So you are rationally allowed to just decide to assign high credence to not being a simulation. You cannot be rationally compelled to think that you must be a simulation. So this kind of argument seems to depend quite sensitively on the assumption that there is some correct way of assigning your credences, and if there is not any such rationally compelling way, this kind of argument is not going to go through. We see a similar kind of thing with arguments about Boltzmann brains in cosmology, such as the one we had yesterday. So there's this sort of class of arguments which says if there is a cosmological theory that predicts that most observers are Boltzmann brains rather than persisting observers, well, then that theory predicts that you should most likely be a Boltzmann brain, and you presumably are not a Boltzmann brain. So that theory is going to have to be rejected because it's empirically inadequate. But again, this argument works only if you assume that you are equally likely to be any of these observers, if you are supposed to think of yourself as being kind of randomly sampled over all of the possible observers in your world. But again, this is a pure self-locating case. All of the centered worlds here are in the same possible world. All of the Boltzmann brains and the non-Boltzmann brains all belong to the same world. So because this is a pure self-locating case, I again want to argue there's no rationally compelling way to assign the credences here. You are not obliged to assign equal credence over the Boltzmann brains and the non-Boltzmann brains. You are free to just decide to assign high credence to not being a Boltzmann brain, regardless of how many Boltzmann brains there are. So that for me means that evidence like this really can't possibly count toward whether or not we should believe the theory, because there's nothing to force us into assigning a certain credences over the Boltzmann brains and the non-Boltzmann brains, and therefore we can't be sort of forced to conclude that this sort of theory is empirically inadequate. We also see a related class of reasoning in cosmology involving sort of anthropic reasoning. These are arguments in which people seek to explain some observed parameter value in our actual universe by saying, well, let's suppose we're in a certain kind of multiverse. Then we're going to do some sort of looking at proportions of multiverses or looking at measures over multiverses and argue that in such a multiverse, the appropriate self-locating credence to assign to finding oneself in a universe with fundamental parameters close to the one we observe is relatively high. So they say, okay, we've explained the value of this parameter. Great, we know why it has that value. Now, it's well known that this runs into problems in the case of an infinite multiverse. It's not obvious how to choose the correct measure that you should use to define your probabilities here, and so the method of making predictions seems to break down. And indeed, what I would argue is that, that's sort of to be expected. There can't possibly be any sort of rationally compelling choice of measure here. We are free to choose any measure that we like, no matter what kind of measures we construct or how nice they are or what properties they have. None of them is ever going to be more rationally compelling than any other one. So we shouldn't sort of expect that the physics is going to dictate a uniquely rational measure to us. Moreover, I think that the same issue even applies in the case where we have finite multiverses. In that case, of course, people have typically assumed that we should just count the number of worlds and assign credences in proportion to the number of worlds. But I want to argue that is not right. We are not rationally compelled to assign equal credences over all of the worlds. That's intuitive and a simple thing to do, but we're not forced to do that. And so even in this case, I want to say there's no sort of objectively rational way to say what the probability is to be in a certain world within that multiverse. So the lesson I take from this is that we should be really cautious about this kind of reasoning and using this kind of approach to explain observations. I think we should be particularly cautious in using this kind of explanation and inference to the best explanation. So people have sometimes tried to use this kind of explanation to convince us that we should believe in the multiverse. They've sort of said, well, the multiverse can explain why the parameter has this value. There's no other good explanation, so we should believe we are really in the multiverse. But it seems to me this kind of explanation is just not robust enough to support that kind of inference. It's relying on an essentially free subjective choice about how you want to assign credences over the worlds in that multiverse. Therefore, doesn't really seem that prediction is sort of robust in the way you would want it to if you want it to be if you're going to use it to infer something very substantive like the existence of a multiverse. Finally, this applies to various cases where people have attempted to use self-locating observations to do empirical confirmation. So this is particularly common in the many worlds interpretation of quantum mechanics, where it seems that most of the observations that you would make of experimental outcomes are going to be self-locating observations about where you are in the branching structure of the universal wave function, rather than sort of non-self-locating information about the world as a whole. So the Everett interpretation, the many worlds interpretation, seems to require that we can, in fact, use those observations to do empirical confirmation, because otherwise we're just not going to ever be able to confirm any scientific theory in that context. However, if there is no rationally compelling way of assigning pure self-locating credences, I think that shows quite straightforwardly that something called the relevance limiting thesis is true for pure self-locating credences. The relevance limiting thesis just says that learning a piece of self-locating information can't give you new information about the world as a whole, and so seeing a piece of self-locating information should never cause you to change your non-self-locating credences. What that means is that if the relevance limiting thesis is true for pure self-locating credences, we just can't use them in empirical confirmation. It is not reasonable to change your beliefs about a scientific theory, for example, on the basis of seeing pure self-locating information. So if this is right, I think that means the many worlds interpretation is in trouble. It seems to imply that we can't empirically confirm any scientific theory in that context. And that, of course, makes the many worlds interpretation self-undermining, because the many worlds interpretation is based on quantum mechanics, which is a scientific theory that is supposed to have been empirically confirmed. So if we can't use self-locating credences in this way, that is going to pose quite a significant threat to that kind of approach. So, to conclude, I know that the claim I'm making is quite counterintuitive for many people. Many people do have this strong intuition that there is some way you should assign these credences in these situations. But I hope I've at least done enough to convince you that we should be perhaps more cautious about using these things than we currently are. We should at least be kind of examining quite carefully the ways in which we're using these credences in reasoning, particularly in the context of physics, and really making certain that we feel the reasoning is sufficiently robust to support the kinds of conclusions we're trying to draw here. So thank you, and I think we should do the comments.
Thank you, Sean. Thank you, Emily, for a great talk. I really enjoyed this. All right, I'm going to try to make you a little bit happier again. So, in the biggest frame, I would say that what you're discussing, Emily, is really, questions to do with our place in the universe. And of course, as a cosmologist, that really interests us. We want to know our history. We want to know why the universe around us is mysteriously biophilic, how we fit in the grand scheme, and so forth. And so you make a distinction, a very clear distinction, I think, between pure self-locating credences and superficially self-locating credences. The first referring to uncertainty about our place in the universe, in a possibly big or even infinite universe. And then the second to do with uncertainty related to, in what kind of universe are we? And so you argue that there's no proper rational way of assigning credences in the first case, whereas the second case seems to be okay. And so that in the first case, we shouldn't even, as cosmologists, we shouldn't even think of trying to predict pure self-locating credences from a proper rational scientific cosmological theory. Now, as a cosmologist, I can't possibly offer meaningful criticisms to your philosophical statements, nor can I add noisy philosophical thoughts. But indeed, I can testify that on many occasions in the last 20 or 30 years, we cosmologists have tried to assign what we felt are rationally compelling credences, pure self-locating credences. And guess what? We failed. So that's interesting. Even Sean got confused about these matters. And the typical case is the one you discussed. We often think about a huge, possibly infinite universe, which consists of many bubble universes. Cosmological inflationary theories seem to predict such kind of huge structure. And then the question arises, in which one of these universes should we find ourselves? And hence, what should our telescopes and our cosmological observations, what should we see? And the usual reasoning has been to apply some form of anthropic reasoning. You select a few features of the world around us that you deem relevant, and you argue we should be typical observers among that set that you've defined. And the problem, of course, is that what I deem relevant or what Sean deems relevant is often very different. And so we don't agree. There's no rational way of agreeing. And indeed, this feeling, this statement, this conclusion has gradually gained acceptance in the cosmological community as well. In fact, we often refer to these your principle of indifference as typicality assumptions, and even here is a paper by Hartel and Srednitsky years ago already, questioning the kind of reasoning based on typicality, that we should be typical observers in one or another respect, arguing also that there's no physical mechanism behind that random selection that is assumed in such reasoning. So gradually it has dawned upon us that the measure problem in inflationary cosmology is indeed not something that's going to have a quick fix, but in fact something that drives at the very roots of physics. Now, what could possibly be a way out? And so in the remaining 6 minutes, I'm going to try to argue for a way out. What's the problem here? The problem is the one we discussed on Thursday. Namely, this is a picture of the universe, an image, a theory of the universe, which is a theory that is built from an Archimedean perspective. We are out of the equations. We are nowhere to be found. And then the anthropic principle is brought in as a non-scientific principle to bring us back in. This is not the kind of unification that we need in cosmology. We are within the universe, looking up and looking out and figuring where we come from. And so the question that I think this problem drives at is, can't we let go of this Archimedean standpoint on the cosmos? Can't we, in a sense, turn cosmology inside out? And so what I'm going to argue is, in fact, that the change from classical thinking of about cosmology, which is what this multiverse kind of thing is, from a proper towards a proper quantum way of thinking about cosmology, is in fact all we need. It offers a way to bring in the observer into equations without falling into the trap of assigning or predicting pure self-locating credences, but in fact only predict superficially what Emily calls superficially self-locating credences. And so I'm going to illustrate the noisy philosophy of Emily with a calculation that does exactly that. The shut up is in brackets because I did the calculation with Hawking, and Hawking never shut up, so I put it up there. Now, if you're going to think quantum mechanically about the universe, and you like Schrödinger's cat and all that, forget about it. You have to get the lab and the experimenter, everything in the box. There's just one grand wave function, and that's what it is. There's no exterior. In fact, this point was made long ago by John Wheeler, who envisioned his famous picture of the history of the universe. Upright is the big upright, yes, is the Big Bang. The universe expands, but then there's this eye and these dotted lines going back into the past to suggest, I think, I wasn't there in those days, but I think what he meant was that the universe, the history of the universe is just a way, even the past is just a wave function. And it's it's countless and countless of observations, interactions, and so forth that gradually sort of crystallize one or another history among the possible histories of the universe in this wave function. And so Wheeler's words resemble very much what Sandra was telling us on Thursday. Now, Wheeler didn't have a model. So this is sort of where it ended. But Hawking and Hartle came up with a model for such a universal wave function long ago. Here is the paper of 1983, Wave Function of the Universe. And the equation may not be very illuminating to you, but in fact the model comes with a very simple geometric picture. Here it is. On the top right, you have the classical expanding universe. There's three space dimensions, but then back down to the left, when you go to the Big Bang and the universe shrinks, essentially their model amounts to turning time into space. Their model amounts to the bold statement that the quantum origin, the initial conditions, can be understood geometrically, but not in terms of Lorentzian geometries that contain a time dimension and causality and three space dimensions, but in terms of purely spatial geometric configurations. And the transition from that quantum origin to that classical expansion from no time to time, that transition, the key prediction of that particular model of the wave function is that the transition occurs through a period of inflation, through a period of rapid accelerated expansion. Now, because this is a wave function, this is not going to be just one unique universe. It's a wave function. It's a function of many different universes. So the way you should think about their model is really as a collection of different possible worlds. Worlds with a lot of inflation, worlds where we can exist, worlds where we cannot exist, and so forth. Just like an electron doesn't have a position before you measure a position, but many possible positions, the universe in quantum cosmology has many possible histories. And they come each with a relative probability. Now, in the 80s, Hawking looked at his wave function from an Archimedean viewpoint, as if he was outside this wave function. And he concluded that the most probable universes were not the ones we can live in. The most probable universes have a brief burst of inflation, they recollapse, they disappear, they're empty, they're lifeless. But then he remembered Wheeler's lesson, that in fact, we are probing the universal wave function from inside. We have a whole list. We are not asking any a priori question. In fact, we're asking a strongly conditioned question. And in certain models of inflation, this more refined question turns this probability distribution around and selects histories that in our past, in fact, have a very strong burst of inflation and agree with predict a number of observations. Now, the key point, to come back to Emily's thoughts, is that those predictions that you get out of these wave functions are not histories of the universe that detail whatever happens far outside anyone's Hubble volume or horizon or whatever. In fact, they're highly, highly coarse-grained histories. They do not make any statement about where we are in any of these possible universes. They make only a statement about in which one of these possible universes we are. And that, if my reading is correct, is precisely the difference that Emily wants to make between pure self-locating uncertainty and superficially self-locating uncertainty. So my statement is that, in fact, doing quantum cosmology properly, quantum mechanically, takes us from the PSL to the SSL credences. Now, there's a bizarre, of course, there's a truly bizarre element here, which was already visible in Wheeler's drawing. Somehow, the history emerges, even though there's no backwards in time communication, the history sort of emerges in retrospect. The past emerges in sort of in a retroactive manner. So if the time, perhaps it is better to think of sort of the emergent time direction backwards. So while Hawking, of course, first thought about it much more in terms of a creation model. Now that backwards in time reasoning sort of connects to also what Nima was talking about on Thursday, to these holographic ideas in physics, in quantum gravity, that one of the dimensions may be rather a holographic projection from emerging from a pure quantum surface theory. In this case, in the cosmological case, holography would work in a way that a time dimension is the emergent one. And the picture that goes with this, and with this I will... This is something like this. The present would be the edge of this disk. Information would be located on the edge of this disk. That would be the present state of the universe. And the past, the Big Bang would be the beginning of the universe, would be the center of this disk. And the past would sort of gradually re-emerge from this quantum mechanical theory that lives on the edge of this disk. How this happens, I have no time to explain, really, but the ideas of holography applied to cosmology seem to point to that in that direction, that in fact the questions that we're asking about the world define or are an integral part of the cosmological theory that we aim to construct. So I want to end with an epistemic thought, sort of throwing the ball back to the philosophers here. The bulk picture, the gravitational picture of these earliest stages of the universe that emerges from this holographic way of thinking about it is the following, I think. You have the late time physical forces, physical laws on the top of this diagram. You go back to the beginnings, various forces unify, and we've always thought, well, we're going to land on some unified theory with a capital T, the truth, sort of the transcendental, physical, mathematical world. But I think this is wrong. I think what holography is suggesting is that this process of simplification, really, of physics goes all the way through, till eventually, at the Big Bang, even the laws of physics evaporate and disappear. And so I think the epistemic readjustment is that we used to think that we had these governing laws of nature, mathematical truths from which the physical universe is emerging. You have a law of initial conditions that creates the universe and eventually observership. But I think the later Hawking turned these arrows around, and holography, with its emergent time, which is its emergent past, in fact, gives support for this. So this is my philosophical thought. I think cosmology ultimately will ask for a generalization, an epistemic generalization of physics, where physics is not just about laws of evolution and dynamics as we know it, but a more general notion of law, which includes the questions we're asking and which includes the initial conditions. And to signal where Emily comes in here, the questions we're asking should be in an SSL frame and not a PSL frame. I do agree with that. Thank you.